In this video, I'm going to introduce the concept of mesh current analysis, and we'll do a single mesh example. Mesh current analysis is based on Kirchhoff's voltage law and Ohm's law. It's equivalent to node voltage analysis, which we've already studied. It's similar in that node voltage analysis uses Kirchhoff's current law and Ohm's law, but here we focus on Kirchhoff's voltage law and Ohm's law. Mesh current analysis is valid for any linear and planar circuit, like node voltage analysis. So here's the outline. We identify meshes. What's a mesh? A mesh is a loop that encloses no other loop in a circuit. Once we have our meshes, we assign a mesh current for each one, and then we write a Kirchhoff's voltage law equation for each mesh. We use Ohm's law then to turn our mesh KVL equations into expressions that have mesh currents and resistances and voltages, any known quantities. And we should have one unknown mesh current for each mesh equation, so we can then solve a system of equations. Finally, we then solve for variables specified by the problem. So let's focus on this one mesh example. We're looking for Vx and Ix as defined in this problem statement. I can define a mesh current. It may or may not be the current in a loop, but in this case I can pick a mesh current that goes clockwise. I could choose counterclockwise. It doesn't matter. I just have to be consistent. So we'll call this I. We have a single mesh, so we have one KVL equation to write around the loop. So for this KVL equation, as we follow that current, if we cross the voltage source, we have a negative 4 volt drop. We might then specify a V1 for completeness, and then we have a V1 drop, and then following this current arrow, we have a negative Vx drop, and then we're back to the low side of the battery where we started, so we put 0. Now we're going to use Ohm's law, and we still have our negative 4 volt drop. Ohm's law, we have I times 3 ohms, so that's our mesh current times 3. And for the next voltage drop, I'm actually going to assign a V2 just to make things easier. And that will mean that it'll look like V2 here instead of minus Vx. I've defined V2 so it follows the passive reference convention. The way that's going to work here is I times 5 equals 0. Okay, so now we rearrange. We have one equation, one unknown, so we can solve for I. So we'll combine the I terms, and we get I equals 1/2 amp. That's enough to find Vx now. Because of the passive reference convention, we can use Vx equals negative I times 5. And then we know that Ix is equal to negative I, negative 1/2 amp. Also, one other thing to do here is to check, right? If I is 1/2 amp and the total resistance here is 8 ohms, you can see that the voltage drop across the two resistors is 8 volts. So we can calculate V1 and V2, and we can see then that we satisfy our Kirchhoff's voltage law equation, where V1 and V2 have to add up to 4 volts.